Hello everyone, I'm Jerry Joseph. I'm here to present the assessment of the subject ENGG955. Welcome to my presentation, Optimization of Welding Temperature. So, what is this welding? Welding is simply the process of joining two metals by heating them and melting them, finally cooling them. But it is different from DNW because it uses two chemically inert or mechanically distinct materials. But every metals cannot be joined together. They need to be compatible in thermal expansion coefficient as well as melting temperature. Why do we use DMWs? It is the simplest method to join two metals with a leak-proof joint. And in many applications, the materials will have a location-dependent property. And using DMW, we can create such a cost-effective and flexible materials. Today, DMW are having an increased demand. But assume it has failed in an operation. It requires both time and money in order to repair such cases. Consider a case of power plant. A damage in a critical equipment can cause the shutdown of this power plant, and it may create a loss of almost lakhs of dollars for every day. In the extreme cases, if it explodes and causes fatalities, it will be dangerous. The material we are going to study is AISI 310, that is a high strength austenitic steel, which is used up to a temperature of 1000 degrees Celsius. And another one is 2.25 chromium molybdenum steel. It is a heat resistance alloy steel, which is used up to a range of 600 degrees Celsius. The main methods that is used for welding is the solid state welding and fusion welding. The friction welding, the temperature does not exceed the solidus limit, but in case it can cause severe heating corrosions and create residual stresses. But in case of fusion welding, it does not limit the material to a particular shape or does not require the use of pressure. The material is heated up to the melting point, but there is one problem, the carbon diffusion. Carbon migration. Due to the difference in concentration of the alloy elements such as chromium, the carbon diffuses from the high carbon concentration to the low carbon concentration. It creates a decarbonized zone. A decarbonized zone is soft and it can fail due to its low strength, whereas the carbon-rich zone, which is developed due to the formation of carboids, can have increased hardness as well as it is brittle. Use of suitable filler materials can reduce this concentration difference. A high carbon filler material can improve the longevity, whereas a low carbon filler can reduce the stress accumulation. The thermal expansion coefficient of such a filler should be between these two base materials. It is most probably recommended to reduce the content of impurities. In certain cases, the nickel can be used to reduce the carbon migration, which is one of the plus point of nickel. The main modes of failures are creep failure in hydrogen assisted cracking, and the failure under tensile load. Creep failure can be described as the growth of minor micro cracks, and when it is subjected to repeated cycles, it grows into a failure. Hydrogen assisted cracking is similar to creep failure, but it is due to the presence of hydrogen in it. It can be reduced using heat treatment process. First one is the preheating process. It can aid in the escape of hydrogen and also reduce the engaged stress. But whereas the post-welding heat treatment are used to relieve the residual stresses in it. It can also refine the microstructure of these welded joints. But it is a time-consuming as well as a costly process. since it is separate from the welding process. This leads to the idea of optimization. Optimization is nothing but finding a most effective method. The optimized parameter can reduce the amount of defects, and it is very cost effective. The major factors that can be optimized are the welding speed and the welding atmosphere, cooling rate, welding temperature, and heat treatment. Consider the welding temperature. The temperature can affect the carbon migration. The higher the temperature, the more will be the carbon migration. And also, due to the difference in expansion coefficients, it can create distortion due to the deferred expansion. And when it is cooled, it causes stress accumulation as well as growth of microcracks. About this, the proper fusion. Without a proper fusion, the weld can function its own properties. This led me to a question. What are the effects of welding temperature, and what is the suitable welding temperature to obtain a sound weld between AISI 310 stainless steel as well as 2.25 chromium molybdenum steel? And this is my research question for my presentation. For finding this, I used a gas tungsten arc welding to weld these two metals, and I created 7 specimens and welded under 7 different temperatures, such as from 950 degrees to 1250 degrees with a step size of 50 degrees. The weld temperature can be varied with the use of current as well as voltage. The preheating of the metals can reduce the microcracks, whereas the post-weld heat treatment is to be avoided since it may assist the carbon migration. The specimen is cooled naturally so as to prevent the microcracks again, and it is subjected to mechanical testing such as shear strength test, tensile strength test, impact test, and hardness test using the standard methods. Finally, the microstructures are analyzed for its proper fusion as well as the mechanical properties of the heat affected zones using a scanning electron microscope. The main plus points of this research is that it considers all the main aspects of the mechanism, such as the lack of fusion, then the carbon migration, then the cracks formation, finally the creep failure. This experimental design can provide a much realistic solution. But as we can see that I already said, the filler materials can properly regulate the quality of welding, but we are unable to investigate on such issues, as well as we are testing it on a room temperature. It is different from the service conditions. Finally, we can say that the temperature control is one of the most affecting factor of a weld quality. Using an optimized welding temperature, we can, in a simple and cost-effective manner, we can reduce the failure of such a mechanism.